Let's take a look at a problem together. Assume you have 16 coins and one of them is fake, and the fake one weighs slightly more than any of the others. If you have a balance scale, the kind that you can put things on both sides of it and it tilts toward the side that's heavier, but you can't use that balance scale more than 4 times. People are busy and need it, or it will break after a certain number of uses. Whatever the reason may be, you can only use it up to 4 times. What could you do to find the fake coin among those 16 coins? We know that we've eliminated the possibility of the straightforward approach of just weighing pairs of coins, because that might take up to 8 times of using the scales. So pause the video for a moment and think about what approach you could take to find the fake coin among these 16 coins using the scale no more than 4 times. One approach that you could take would be to split the coins into halves, into groups of 8, and then to weigh those groups of 8 against each other. And if one group is heavier than the other, then that means that the fake is in that heavier group. So let's say that in our case, this right-hand group was the heavier one. Then I could repeat my process and split that group into groups of 4 and weigh those 4s against each other. And if, say, this left-hand group of 4 was heavier, then I could split those into pairs, into groups of 2, and weigh those pairs against each other. And let's say that this pair was the heavier one, so I can weigh each of those coins against the other. And whichever of those 2 coins weighs more, we now know is the fake. And you can see here that it took 1 time of using the scales to narrow down to 8 coins. It took another time, 2 times of using the scales to narrow down to 4 coins, and 3 times to use the scales to narrow down to 2 coins, and then 1/4 and final time to find the fake among those. If you enjoy a challenge, there are some ways to find it faster than 4 comparisons, 4 times of using the scales in a problem like this, but that's not what we're focused on. What we are going to focus on is the actual approach and thinking about what it means to take an approach like that. So we'll call it find fake, and it's given some set of coins. And when we're given that set of coins, what did we do? Well, we split the coins into halves. We weighed the halves. And we repeated the process on whichever half was heavier. So we could represent that as calling find fake on the heavier half. This approach repeats that same process of splitting, weighing, and then finding the fake among the heavier half to do its own work. It's referring to itself. There's one little trick that we had to do here to be able to stop, though, because we stopped when we found one coin that was heavier than its partner in a pair. So we could say, if there is only one coin remaining, then we've found the fake. That's our fake, and we can stop. So if there's only one coin remaining, stop, because that's our fake. Otherwise, we do the splitting and the weighing and the finding the fake. You can think of this like an else here. And that gives us an approach that could work on this in actual code, if we could represent the coins somehow as, say, an array or some other data structure, we could do this in code. Now, I mentioned before, the findFake function or method refers to itself. It uses itself to solve its own problem. You may have learned a word for this in the past in math classes, and that is recursion, or a recursive function. So many people remember the most important thing about recursion to be that it's a function or a method that calls itself or refers to itself. I'll limit it here to saying it's a function that calls itself. But what's important for our purposes when using recursion to solve problems is that it is a function that calls itself with a simpler version of the problem until it reaches a base case. I want to take that term, base case, and break that down a little bit too. A base case is like our situation here at the top. We knew we could stop because we already had the answer right away. There was no more work that needed to be done. We did not need to split that one coin in half and weigh those halves. We knew we were done. So a base case is when all the work is done, or rather when a solution can be found with no more work. We are done. We can just return that solution, and the base case has essentially that one job. See that the solution is already at hand and return it or give it back or say you're stopping and you're done. The other piece that recursion requires is a recursive case. So a recursive case is basically the opposite of the base case. When more work needs to be done to find a solution. So we take some step to simplify the problem and then call recursively with that simpler version of the problem. Or less of our data, for instance, in the case of these coins, we have less data after the first call. We're in the recursive case down here where we don't have an answer right away. I can't tell you which is the fake just because I narrowed it down to 8. So I'm in the recursive case. I do some step or some work, like splitting the coins into halves and weighing them. And then I call recursively with this simpler version of the problem or with less of the data. And this is the basic structure that you're going to find in essentially every recursive function, every recursive method that you write or that you see as an example. Sometimes they will look a little different in terms of what's written first or what the base case is or what the step is to simplify in the recursive case, but they'll all follow this same basic structure. Some base case that you're trying to get to where there's no work left to be done, and some recursive case where we know more work needs to be done and we take some step that should get us one step closer to our base case or a little bit closer to reaching our base case, and then we call recursively with that simpler version of the problem, and we'll repeat this process as many times as are necessary. If we forget to write a base case, then we'll be calling the function over and over forever until our program runs out of memory. And if our recursive case's step is wrong and doesn't get us closer to the base case each time, then similarly, we'll be calling recursively forever and never stop until we run out of memory. One thing that people often find challenging when they're first starting out with recursive functions is that you have to trust that the recursive call that you write in is going to do its job. When I call find fake on all the coins, and then I split and I weigh, I have to trust that my call to find fake with half the coins would return me the actual fake as a result. And sometimes I may have to trust in other ways that recursive call will do its work. Now, on the one hand, this should be simple because we call functions all the time that we haven't seen the code of, and we trust that they'll do the job that they're supposed to do. However, this can be mentally challenging for people when it comes to recursion because you're the one writing the method and you know you're not done writing it yet. And so this can challenge you to have to take this leap of faith. It's referred sometimes as the recursive leap of faith, where you have to treat it just like any other function and assume that if I call find fake with some smaller set of coins, it will actually do its job and find the fake among that smaller set of coins. Or if I ask to get the sum of part of my remaining array, then I have to trust that sum function, when called recursively, will give me the right result from that sum of the rest of the array. And it will do that if you have designed it with this right structure of a base case where we know to stop because we have our answer right away, and these recursive cases that take a step to get us a little bit closer to that base case and call recursively on that simpler version of the function. And you'll see plenty of examples of these as you work through the Recursion 1 activity.